All right, we're going to go ahead and get started. Most of you know me. My name is Bill Corey. Today we're going to talk about advanced motors. What we're really going to talk about here is what is the power factor and how to select the right size wire, and also how to do testing on the motors. So these are some very important things, and that's why we kind of saved them for this last webinar on motors. So we're going to start out by talking about single phase. And when we look at single phase, again, I kind of showed you this, I forget if it was last week or the week before, but when you look at single phase, what you're really looking at here is the movement of plus or minus, and we're going back to zero, all right? So we're making a circuit or completing a circle here, all right? When you have three-phase, and I have to admit I prefer three-phase better myself, you're going to notice that you actually have three different sine waves. There's going to be this first sine wave here, which makes it 360 degrees. Within 120 degrees of that, the second sine wave starts, and it makes it 360 degrees. And then within another 120 degrees of that, the third sine wave starts, and it makes it 360 degrees. Now, we're going to back that third one up a little bit, just because there's something that we want to show you here. What we want to show you is this, and this is why three-phase is actually the best. And we'll take a look at this again a little later on, because it's that important, okay? When you look at three-phase, you're going to notice that there's always going to be two positives and a negative, or there's going to be two negatives and a positive. So during that 360 degrees, one cycle of one of those phases there, you're going to get two negatives and a positive, or two positives and a negative. That's going to determine your rotation, and we'll talk more about that a little later on, okay? So to get started with, we're going to take a look at Ohm's Law. Ohm's Law was the original pie chart. So you'll notice here, we've got P, I, and E. P stands for power or watts. I stands for current or amps. E stands for voltage. All right? The laws look like this, and there's one in particular that's very important to us, and that's that first one there. P equals I times E. All right? So what it's basically saying is amps times volts equal watts. Now, there's a total of 12 laws altogether. 6 of them are meaningful to us, so I didn't put the other 6 in here. And of the 6 that are meaningful, that top one is the most important one. All right? Now, you've heard the term power factor in the past, perhaps. And, of course, I've been doing this now for 21 years. And I remember when I first started doing it, I would ask the engineers, okay, what's power factor? And everybody came up with this, it's a magical number. You want to be within 90%, but nobody can really do it kind of stuff. And, of course, I asked our engineers at Stay-Right. I asked the engineers at A.O. Smith, because we were using A.O. Smith motors. I asked the engineers at Franklin, because I was using Franklin motors at the time. And none of them could really tell me what power factor was. We finally hired a man. His name is Peter Hennig, and Peter is our electrical engineer now, has been for about 7 or 8 years. And Peter actually gave me the formula. He pulled out a book, and he gave me a formula. And the formula says power factor equals real power divided by apparent power. That's what power factor is. So we're going to look on page 13 of the PN 793, if you've got that book handy. If you don't, you can just follow along on the screen. I've got all the information here. And we're going to look at model number P42B000582. And if you look on the chart, it's that motor right there, okay? You can tell by looking at it that it's a half horsepower motor. It's 230 volt. Interestingly, it says the kW is 0.37. 0.37 is the kW. Now, I want you to know that 1 horsepower can be defined in many, many ways. One of the ways we define 1 horsepower is 746 watts. So if 1 horsepower is 746 watts, and I take half a horsepower, so that would be 1/2 times 746, I would wind up with 373 watts, which if you divide by 1,000, comes out to 0.37 kilowatts. And that's how you come up with that. So what that 0.37 means is 1/2 horsepower. That's what it's actually equaling. 0.37 equals 1/2 horsepower. All right? You'll notice, though, if you look over in the chart where it says full load, the actual measured amount of watts was 834. Now, again, this is at full load. Full load means that we're at 1/2 horsepower. All right? If you look all the way over at maximum load means the absolute maximum amount of work that you can get out of that motor without burning it up. And that's going to cost you 1,073 watts to get that maximum load out of there. Now we're going to take a look at that maximum load. So we'll start out again reminding you the power factor is real power divided by apparent power. And we'll also remind you that we are on page 13. We're looking at the P42B00005A2, which is the 1/2 horsepower 230 volt motor here. All right? Maximum or service factor load, the amperage is 4.7. Now remember what Ohm's law was. Volts times amps equal watts. So if we take the volts times the service factor amps, okay, so our volts are 230, our service factor amps are 4.7, we get our service factor watts of 1081. And of course, if you look up there in the book, you'll notice it says 1073. Now, does everybody understand why it says 1073? Remember what I said, this is a measured amount of watts, okay? So that's real power. Ohm's law is apparent power. So if we take Ohm's law, we take the real power, we divide it by the apparent power, we come up with a power factor of 99.25%. All right? Everybody understand that? Now you also have to remember that you're looking at 1.6 service factor here. So if you were to take 1.6 times 0.37, you're going to come up with a little over 600 watts, or close to 600 watts, which again is going to leave you 400 some watts. And what are those 400 watts? Well, last week I told you to remember that. When we look at the light bulb, what do we get? We got light and heat. So that extra wattage is heat that we're losing, okay? Something that we're paying for that we're really not getting a whole lot of use out of. All right? Now, if we look at the next page here, page 15, we're going to find, it says single-phase 4-inch motors, electrical parameters, and of course there's a lot of information here. There's the motor that we're looking at, and over here it says percentage of power factor. Now remember, at service factor it was 99, all right? You'll notice, though, at full load, it's only 97. Now, of course, this teaches us something. What it teaches us is that motors like to run at service factor. They like to run in their service factor a little bit. They become better. If you look over at efficiency, which is the next one there, you'll see that they're even more efficient when they're at service factor horsepower. Now, I've compressed the charts a little bit, so if you're actually looking in the book, you're not going to find all, you're going to find more than what I have on the screen here. I compressed the charts a little bit, and you'll see we're looking at the CSIR. Remember, CSIR means cap start induction run control box. We're looking at the same motor, only this time it's a 3-wire instead of a 2-wire. So there is a difference between the motors. And you'll notice the service factor power factor is only 71%. And you'll notice that the full load service factor power factor is 58%. All right? A considerable distance less. And of course, we're wondering why. Well, part of the reason is, when you look at the two-wire motor, remember it is a PSC motor. PSC means permanent split capacitor. So what that means is there is indeed a capacitor built in the bottom of this motor. Because there is a capacitor built in the bottom of the motor, that means that we've got a better running. Now, of course, in our CSIR, there is no running capacitor. And that starting capacitor gets taken out of play, and now you're only running on the main windings. Hence, the poorer power factor, okay? Now, when we take that same three-wire motor, because remember, you can run a three-wire motor CSIR, or you can run it CSCR. So if we take that same motor, and we run it with a cap start, cap run control box, now you'll notice that our power factor percentage went up to 85% for service factor, and it went up to 76% for our full load. Now, of course, it still isn't 99 and 97, yet both the PSC and the CSCR have running capacitors in them. So what's the difference now? And the difference now is the placement of the running capacitor. Remember, in the two-wire motor, the running capacitor is built into the bottom of the motor. When you look at the three-wire motor, your running capacitor is built into the control box, which could be hundreds of feet away, and that's what's going to cause the power factor to diminish a little bit. So even though it's not what the electric company would really like, it's better than if you're running CSIR. And that's another reason not to use the CSIR control box. All right? Now, let's take a look at what I meant when I said the actual or service factor horsepower. Because when we get a motor, we can call that motor anything we want as long as the service factor is not below 1. Most motors, especially over 3 horsepower, have a 1.15 service factor, or they have the ability to handle 115% of what their nameplate horsepower says. So to calculate service factor horsepower, all you have to do is simply multiply the nameplate horsepower by the service factor, and you will get the service factor horsepower, or the actual horsepower that we started out with. So on that half horsepower two-wire motor, and by the way, it doesn't matter whether it's two-wire or three-wire, the service factor was 1.6. So if I take 0.5 times 1.6, I wind up with 0.8 service factor horsepower. Now, if we go to the 1.5 horsepower motor, it's got a 1.3 service factor, and so, of course, if you multiply 1.5 times 1.3, you come up with 1.95 service factor horsepower. And all I'm really doing here is just showing you two different ways. You can either spell it out or you can use the abbreviations, either way, and that's going to be your service factor horsepower. All right? Now, next thing we want to look at is something called brake horsepower. Brake horsepower. When you look at the formula for brake horsepower, you see it says BHP equals GPM times TDH times SG divided by 3960 times the efficiency. Okay? What does it all stand for? BHP stands for brake horsepower. Brake horsepower is the amount of horsepower used to do the job at the time. Remember, if your flow rate changes, if your head changes, that's going to change your brake horsepower. All right? So it's the amount of horsepower required to do the job that we're attempting to do here. Okay? GPM obviously means gallons per minute. TDH stands for your total dynamic head. That's all the losses in the system. SG stands for specific gravity of a liquid. The specific gravity of fresh water is 1. 1 times any number is that number. So in most cases, especially if I know that I'm doing a freshwater application, I will not include specific gravity in the formula just because it confuses people. But if I'm going to change and I'm going to pump alcohol, for example, alcohol weighs less than fresh water. It's only about 80%. So that means I only need about 80% of the horsepower to do the job. If I was going to pump salt water has a 1.2 specific gravity. So now I need 20% more energy to do the same job if I'm going to pump salt water. So this is why you need to know the specific gravity. But again, if you're pumping fresh water, I don't worry about it. 3960 is a constant. It's derived from the fact that 1 horsepower also equals 33,000 foot-pounds. And if you divide the 33,000 by the weight of 1 gallon of water, you come up with this constant. So it's a way of converting horsepower, flow into horsepower. All right? And then the last thing there is the efficiency percentage of the pump. And again, this can be difficult to come by. On your smaller pumps, they normally do not put it. It's usually on your larger pumps that you're going to find the efficiency range. On your smaller pumps, I'll give you an average. Straight centrifugals, you're usually looking at 60 to 80%. Self-priming pumps and perhaps submersibles are going to run in the 50 to 70%. And then you get into jet pumps, which are extremely inefficient because you're recirculating water, and now you're looking at 30 to 50%. So, all right, now, what we're going to do is an actual problem. In our problem, the engineer is telling us that he wants to do 40 gallons a minute, and he wants to put it 200 feet straight up in the air. So according to our formula, we take the GPMs times the TDH. We're using fresh water, so we're not putting specific gravity in there. So 40 times 200 is going to be 8,000. All right? Our engineer specifies that he wants a pump that is at least 70% efficient. So if you take 3960 times 0.7, you come up with 2772. Now, this is the second problem that I've done. So the first problem was to multiply 40 times 200. The second problem was to multiply 3960 times 0.7. The third problem says, let's divide the 8,000 by the 2772. That's going to equal 2.89. Well, it's actually 2.886. We'll round it off to 2.89. And when I talk to my customer, I'm going to say 3 horsepower. It takes 3 horsepower to push 40 gallons a minute, 200 feet straight up in the air. If you're using a calculator, the sequence is just a little bit different. So you'll notice, now you're going to take the gallons per minute times the TDH, divided by times the SG, divided by the 3960 constant, and then divide that by the efficiency, and you'll get the exact same number. All right? So it all depends on how you want to do it. It's totally up to you. All right? Now, the next thing I want to talk about here is Hydraulics 101 taught us that flow and velocity were tied hand in hand. So because of that, with a little bit of math, we can calculate the flow by the velocity. So what we're looking at here is we're looking at a chart that tells us how many gallons a minute need to go past a motor to keep it cool. Now I want you to understand we are looking at a 0.25 velocity. So with a 4-inch ID casing, well casing, you'd have to put a flow rate past the motor. And with 4-inch, that flow rate is going to be 1.2 gallons per minute. So you need 1.2 gallons per minute going past the motor to keep it cool. All right? I don't think I'm going to find that to be a problem anyplace. If I'm going to use a 5-inch casing, now I need 7 gallons a minute going past there. If I'm going to use a 6-inch casing, then I'm going to require 13 gallons a minute going past the motor. And here's where I start to get a little bit worried, because it's not unusual to put a 4-inch pump down a 6-inch well. But if that pump isn't pumping at least 13 gallons a minute, now I do want to point one more thing out. You'll notice it says at the minimum cooling for water flow over 3 horsepower. What they're really talking about here is continuous duty. If you have a continuous duty pump, then you want that pump to be cooled, that motor to be cooled. So what we're really looking at here is continuous duty. And hopefully, if you're putting a 4-inch pump in a 6-inch well on a continuous duty application, you're going to be pumping more than 13 gallons a minute, okay? Putting a pump in a 10-inch well requires 50 gallons a minute, and this really gets kind of scary. So again, you may have to, when you get to this kind of an application, you may have to put a sleeve on there. You can see the sleeve that we made is a homemade sleeve here. There's actually a better way of doing it. You can put a well cap on top of the discharge pipe and then drop well casing, smaller well casing, over the pump. You'll notice in the bottom there are some bolts, and those bolts are going to center that pump in that second well casing. All right? Now, a question came up back in 2005. It was around February or so. I had been invited to do a presentation for the NGWA in December. I was a part of a panel of 4 trainers, and when we were finished in February of that year, the head of the NGWA sent an email out and said, what is the standard lifetime of a submersible system? And lots of emails came back saying 7 to 10 years, 7 to 10 years, 7 to 10 years, and that's believed to be true, that the average length of a submersible system should be 7 to 10 years. There was one reply that came back that said, wait a second, if you do things differently, in other words, you get the right pump for the job, okay? You make sure that when you pick that right pump, you also put in the right motor, that you've got the right size pipe, or tank rather, going down, sitting up on top. You've got the right size pipe going down the well, and of course the correct size wire. If you've got all this in place, why wouldn't you get about 20 years out of that system? Now, of course, nobody's going to guarantee a system for 20 years, but I do have to tell you that I just got an email yesterday from one of our customers who said that he had pulled a Stay-Right pump out of a well that was 50 years old. He wanted to know if I wanted it back, and I said, absolutely. So we're going to get that pump back and use it on display, okay? Because there's no reason for systems not to last longer than 7 to 10 years, with the exception that people don't properly size the tank, they don't use the correct size pipe, and sometimes they use the wrong wire. And so because they do that, even though they may have the right pump and the right motor, that system's only going to last 7 to 10 years. All right? Now, the next thing I want to talk about here is protecting the pump, and we're going to do single-phase protection first. And so we have a device, it's called the SPP, single-phase protection. It protects against different things. For example, dry run. Dry run simply means we have a plug screen, a low recovering well, or an oversized pump in the well. If you have any of these things taking place, what's happening? You are starving the pump from water. And so because you're starving the pump from water, what it means is you've run out of water and basically you've lost prime. And we call that dry run. You're running the pump with no water in it. Okay? A similar situation is called deadhead. Now, deadhead is similar to dry run. In other words, it's going to look to the single-phase protection, the SPP, the same. The difference is, while dry run happens on the suction side of the pump, deadhead happens on the discharge side of the pump. So it constitutes something that is plugging up the discharge side. So we may have a faulty pressure switch that has welded itself together and not turning off. We may have a faulty solenoid valve that has not opened up, but there's something on the discharge side of the pump that does not allow the flow of water. Now, both of those are going to react to the SPP the same way. They're both going to show low amperage. All right? The next thing we're going to look at here is a jammed impeller, and what a jammed impeller really means is that we can't get rotation. Something has stopped rotation. And so because it's making it difficult to rotate, it takes more power to do that, and the SPP is going to say, wait a second, now we're way over on our amperage. All right? The last thing we're going to look at here is something called over or under voltage. And over or under voltage can be caused by undersized wire. If your wire is too small, that can cause under or over voltage. If you have a high ambient temperature, now some people say, well, it's a submersible pump. Where am I getting a high ambient temperature? If you have a 3-wire pump and that control box is on a post in the sunlight, that's going to be high ambient temperature. If you have an above ground pump and that pump is sitting in the sunlight, that's going to cause unusually high ambient temperature. So undersized wire and high ambient temperature are things that you have control over, and you need to watch to make sure you're doing that correctly. The third thing that can cause over or under voltage is the power company. And that's something you don't have any control over and quite often can't get any help with. So those are the things that you're protecting against. Now remember, with dry run and deadhead, your amperage is going to be low. The SPP is going to ask you to calibrate it. When you calibrate it, it will say, okay, now I'm going to work on 80% under and 125% over. So as long as your calibration falls within that range of 80 to 125%, everything works fine. When you drop below 80%, it's going to assume you either have dry run or deadhead. If it goes over 125%, it's going to assume you have a jammed impeller, or it could be under or over voltage. Because remember, under or over voltage is going to cause high amperage. So two of them will trip on one thing and the other two will trip on the other thing. There is one more thing that the SPP watches out for. I didn't put it on the slide here, and that is too many starts. If you start the pump more than 4 times in an hour, that's too many starts. Or 4 times in a minute, that's too many starts. And it will say something's wrong. All right? Now, when you're doing tests, there are 2 types of tests you do. There are live electric tests and there are electric off tests. Live electric tests include voltage reading and amperage reading. You can only get those when the pump is on and the motor is turning. And you can see by the picture here, there is our amp probe. You can take your amp probe and put it around L1 or L2. You'll get an amp reading there. You can put it around red, yellow, and black. You get an amp reading there. Yellow is the most important one if you're going to use the colored wires from the motor. And the reason is yellow is the return. Everything's going down on black and red and coming up on yellow, and so yellow is your return wire. It will directly be connected to L2. So if you're going to do a live amperage test, that's what you're going to do. Voltage test, once again, you can get right on L1 or L2. Instead of using your amp probe there, you'll plug your leads into it and you'll set it for volts. Okay? Typically speaking, it is to your advantage to set it a little bit higher than what you think it's going to be, because if you set it for what you think it's going to be and it's higher than it should be, that can ruin your meter. You don't want that to happen. All right? The next thing we're going to look at here is an example. When we do our factory school, we actually walk you through all the examples. I'm just going to go through example 4 here today, because example 4 is all about wire sizing. Wire sizing is very, very important. You may remember that the SPP is sensing for things, and one of the things I said it was sensing for was over-under voltage, and over-under voltage could be caused by the wrong size cable being installed. So we want to select a submersible pump cable that will supply a 1.5 horsepower single-phase 230-volt pump with 395 feet of cable. We made this first one simple. Okay? So to do this and find the cable size we need to go to our chart. You'll notice here that the chart is on page 19 of the PN793, the current PN793. It is changing. We are going to look at the CSCR control boxes because of the fact that we're using 1.5 horse. Remember, 1 horse or less can be run on cap start cap run, but it can also be run on cap start induction run. And yes, that will make a difference in your wire size. I'm going to show you that. So we look at the 1.5 horse motor here. There's your motor horsepower there. If we pick the 1.5 horse, up on the top there, that is your wire sizes. Okay? So we pick the 1.5 horse motor, and we go and ask ourselves the question, will number 14 wire work? And of course, if you look at number 14 wire, just cross those two, you'll see that you've got 197 feet, and since we want 395, this is just a little bit short. Okay? So then we go over to number 12 wire, and we look down the number 12 wire and see where it crosses the 1.5 horsepower, and you'll see it goes 314, still short of our 395. We have to have a wire that is over 395. So we go to number 10 wire, and we see that number 10 wire can go 501 feet. That is sufficiently over that I'm very satisfied that number 10 would be the wire that I would choose. So if I go back and I answer the question, I'm going to say number 10 wire would be the correct answer. All right? Now, there is one other thing I wanted to mention, because I already kind of did say it to you, and that is when you're looking at the cap start, cap run control boxes. Remember, 1 through 1.5 horsepower can use cap start cap run or cap start induction run. We are on the cap start cap run. If you look at number 14 wire, you'll notice 1 horsepower will go 304 feet. All right? Now, these are based on NEC standard and the temperature rating of our motor. So they will be different in different charts. All right? This is our chart. If you look at the CSIR control box, you're going to find here that when you look at the 1 horsepower now and number 14 wire, it can only go 226 feet. That's about 80 feet less. All right? So when your customer, if you're a distributor, if you're an installer, when you install this, some installers purposely use cap start induction run control boxes because they think they're saving their customer money. I can save you $20 on this control box. But if I need 250 feet of wire, now I've got to go to number 12. Tell me 250 feet of number 12 is cheaper than the $20 difference between the control boxes. And I know you can't tell me that because it's not true. All right? So this is why I always encourage the use of cap start, cap run control boxes. All right, let's do question 2 on example 4. It says, select a submersible pump cable that will supply a 5 horsepower single phase 230-volt pump with 530 feet of cable. There is a kicker. The kicker is there is 160 feet of number 8 cable currently in place. It doesn't say it in the paragraph here, but it's under the, most of it's underneath the parking lot. The electrician has tested this 160 feet of number 8 cable, says there's nothing wrong with it, it's still in very good condition, and so the owner says, if you're going to replace that cable, you're going to pay for it, because I'm not. I know that's good cable in there. So the question is, what should the remaining 370 feet of cable be? Now, of course, the biggest problem is, where do you start with a problem like this? And the first question you want to ask yourself is, okay, so since I've already got number 8 cable installed, 160 feet of it, what is the overall length requirement of 5 horsepower on number 8 cable? So we're going to go back to our chart again, and we're going to look at 5 horsepower. We're going to look at number 8 wire, and we find that the chart tells us 326 feet. That's the longest distance that number 8 wire can go on a 5 horsepower without causing diminished electrical supply to your motor. Now, that being the case, the next question that really needs to be asked then is, what percentage have we already used? Remember, I need to get 100% of the electricity down and back to that motor. So, of course, I'm going to ask myself the question, what percentage did I use? Now, for those of you that don't know how to do the math, you simply divide the lower amount that I've already used by the higher amount, which is my maximum, and that's going to tell me what I've already used. And you can see here, when I do the math, I've already used 49% of that cable, which means that 51% of the next cable I choose has to equal 370 feet, because I need 370 feet of the next cable size to be 51% of my electric. Now, there's a couple different ways of doing this. I am only going to show you the easy way. The easy way says, let's take that 370 feet of cable that we need and divide it by the 51% that we need. That's going to give us a big number. In this case, that number is 726. So now I can just go to the cable sizing chart. I find 5 horsepower. I find the first wire size that is over 726. It happens to be A09, and I find that I need number 4 wire here. All right? Now, for those of you paying close attention, you may notice that if you did want to change all the cable out, you would still have to go with number 4 wire. So what's cheaper? 537 feet or the 370 feet that we need here? So we can probably all agree that it'd be best to go ahead and use that number 8 wire as long as the electrician said it was good. And from that point on, we'll have to go with number 4 wire. All right? Now, of course, we want to look and see what all is going on here. Okay? So, when we look at the system, our system looks like this. We've got a main breaker box, and we're coming out to our disconnect switch. From our disconnect switch, we go underneath the parking lot, and we've gone 160 feet with number 8 cable. Now, of course, anybody that knows anything about wire size knows that number 4 wire is really big. Okay? So since number 4 wire is really big, we need to install a junction box here so that we can go ahead and connect the number 4 to the number 8. So we connect the number 4 to the number 8, we connect it to our pump, and we put it down in the well. All right? Now, I've had a few people, well, maybe more than a few people say, well, wait a second, shouldn't the bigger wire come first? And I'm going to tell you a little secret. If that number 8 wire is underground, it's probably in a conduit, and that conduit probably isn't much bigger than the number 8 wire, which means you're not going to get the number 4 wire through it. Okay? but they're wondering, well, shouldn't the number 4 wire come first, so that way you have the most power on the biggest piece of wire? And of course, the answer is, well, let's look and see how that electricity is moving. And so when we look at how the electricity is moving here, we see that what's happening here is the electricity is going down and coming back. Whoop, one time too many. Sorry, I'm going to go back here. So the electricity is going down on one and coming back on the other. So we're going down on the number 8, we're coming down on the number 4 once we get to the junction box. But once we leave the motor, we come back on number 4, and then we come back on number 8. So does it really matter which wire comes first? And the answer is no. It doesn't really matter which wire comes first. All right? Now, the next thing we're going to look at here is we're looking at our A.O. Smith dual voltage motor. Dual voltage means that we can run it on 115 or we can run it 230. This is a 2-pole motor. There are 2 main windings here plus a start winding, or some people call it a phase. All right? When you run those windings parallel, you are running 115 volt. When you are running them in series, you're running 230 volt. We saw that last week as we went through the wiring of the motor. Okay? So, some things you should and shouldn't do. You should not do this. In some locations, especially if you're down in Florida, perhaps you're in Southern California or Texas, Southern Mississippi, Arizona, someplace like that, where you've got some really hot weather, putting the pump out in the sun is not a good idea. And so because it's not a good idea, we're going to strongly encourage you not to do that. Okay? But what we would suggest is putting a doghouse over the top of the pump. Of course, you probably have already guessed that if your doghouse has the ventilation plugged, because it looks like you've got a piece of wood or cardboard up against the one vent on the right-hand side, and the other vent has paint cans up against it. And then, of course, we also went ahead and put a blanket on top of the motor. That's doing anything but cooling it. What you want is you want this. You want that doghouse to be at least a foot away from the motor all the way around, and then you want to make sure that there's air threshing through there so that you keep that motor cool. So keep your vents open. The only thing that should be in that doghouse is the pump and tank. All right? We get this call every once in a while in customer service. Somebody will call up and they'll say, "Oh my God, my motor is so hot, can't even keep my hand on it." And of course, at that point, I tell them, don't put your hand on the motor, it's hot. I want you to understand that the outside skin of that A.O. Smith motor can get up to 165 degrees. I don't know anybody that can comfortably keep their hand on 165 degrees. Remember last week when we looked at the motors, there were vents in the bottom that allowed air to get pulled in up by the pump end and come out by the command end here, okay? And so that air circulates, but even that skin of that motor is right on that stator, and so heat transfers that way too, and you disperse some of that heat that way. So you cannot tell by touching that motor that it's too hot. That's for the controls, and in particular, the overload protector. The whole purpose of that overload protector is to make sure that motor doesn't get too hot, not your hand, okay? Now, we also want to talk a little bit here about the nameplate on the motor. Several years ago, we switched from having a pump model nameplate right on the pump to a nameplate that was just on the motor. And so, of course, by doing so, we moved the pump model onto the nameplate of the motor. Now, we tried to discourage the engineers from doing this, but the money savings was too great, and so we were outvoted. The point that I'm trying to make here is simply this. In customer service, we do get phone calls from people who wants us to help them with their pump, and when we ask them what pump they have no clue. And the reason being is that the motor was changed. And when the motor was changed, they took away that pump model number, and nobody ever recorded it after that. So it's very important that you record that pump model number someplace else. If you can, put some indelible marker right on the pump itself and write down the pump model number on there. If you've got a tank nearby, it might not hurt to take an indelible writer or marker and put the pump model number there so that you've got that pump model number at all times. If you want parts, it's the pump model number that we need. If you're looking for a warranty, the salesman is going to need not only the pump model number, but the code number underneath it. They've changed the code just a smidge. They've added a 00 to the 1. You'll see this code number is 1F99C. They've added a 00 to it, and they've added some things after the C. The important part is the 1F99C. 1 means it was made in Delavan, Wisconsin. F is the month of the year. We go A, B, C, D, E, F, June. 99 is the year, and C is the work day of the month. So C is the third letter of the alphabet. That makes it the third work day of June. It does not necessarily have to be June 3rd. It's the third work day of June. All right? Then you'll notice there's a motor model number on there. If you want parts for the motor, that's the number that we need. And then comes the pertinent information about the motor. Its nameplate horsepower is 3/4 horse. Its kilowatts is 55.55, which happens to be 3/4 horsepower, by the way. The voltage is 115/230. The RPMs are 3450. It is single phase, 60 hertz. Code J refers to the fact of the transformer required to run it. Usually that's nothing that you need to concern yourself with. Maximum load amps. You'll notice maximum load amps also have a slash in there. The 12.4 refers to if I'm going to run it at 115 volts. The 6.2 refers to if I'm going to run it at 230 volts. So again, you will notice you will half your amperage if you double your voltage. All right? And then comes that sweet number, SF, service factor. Service factor. All right? So, what does it mean? Well, remember we said the nameplate horsepower times the service factor would give us the service factor or actual horsepower of the motor. And so you'll see here that we've got a 1.65 horsepower motor. Now, if I take a 1.5 horsepower motor that's got a service factor of 1.1, we have an actual horsepower of 1.65. You will find this happening in jet pumps, and jet pumps only. We do not do this with any other pump, only the jet pump, but there are a few lines out there. For example, our HN is called the high service factor, designated shallow well. The SN is considered the standard service factor, designated shallow well. They're basically the same pump, except that we've changed the service factor on the motor, which means we've changed the horsepower. And yes, you can look in any of your catalogs and see that that happens there. Your Berkeley Stay-Right air motor. Okay? This is where you get in trouble with the service factor or actual horsepower. If you have a 1.25 service factor motor, and it's a 1 horsepower, the actual horsepower is 1.25. Okay? If you have a 3/4 horsepower motor, but it's got a 1.95 service factor, then you're going to find that it actually has a 1.46 horsepower. Now remember that the impeller is based on the actual or service factor horsepower, not the nameplate horsepower. So in this particular case, if I had that 3/4 horsepower pump and the motor went out and I changed the motor out, and the guy said to me, well, I don't have a 3/4 horsepower motor, but I've got a 1 horsepower, take that, it's bigger, and you put this 1 horsepower motor on that 3/4 horsepower pump, if you happen to work in that area where you're drawing more than 1 1/4 horsepower, you will burn the motor up. And of course, it's much easier to do because now you've got a pump that demands 1.46 at maximum flow. Remember, we said motors like to work in horsepower or service factor. All right, now, this is going to talk a little more about wire sizing again. What we have here is I had a customer call me up one time. He had a pump sitting out there on a pier. His complaint was that when the pump started up on the sprinkler system, it ran just fine. But what would eventually happen is the pump would turn off. Even though the sprinkler system was still on, the pump would turn off. It would stay off for, 5 or 10 minutes, then it would come back on, stay on for 5 or 10 minutes, then turn back off again. He'd say, what's going on? And so I said, well, it's probably tripping on the overload. So I asked him what voltage he had, and he told me 115. I made really sure that he did have 115 volts. Everybody knows how to do that, right? You ask the question, did you take the back cover off the motor? If they can't answer that question with a yes, then they didn't change it to 115 volts. Okay? Because almost all of the 230, 115 volt motors we ship out at 230 volts. If they do go out at 115, they're going to have a red label on them saying this has been wired for 115 volts. So once he convinced me that he had 115 volts going to the motor, my next question was, okay, tell me about your system. So he said that he came out from the house, from the main breaker box, with 120 feet of number 12 wire, and he was running an HMSF. That's a 1.5-horse two-stage pump. It's a very good sprinkler pump, very good application for it, but obviously he was having a problem. So I got out my book and I looked up wire size, okay? When you look in the book here, now of course we're looking in the A.O. Smith book. There's a similar chart in the owner's manual. You'll notice that it says here, 1.5 horse, 115 volt, 0 to 100 feet, I need number 8 wire. 101 to 200 feet, I need number 6. Now, of course, I know what to tell him to do, and so I say to him, to solve this problem, you need to dig up all that number 12 wire and put in number 6. And he's like, wait a second, I just finished landscaping. I don't want to dig all that wire up. Okay. Then what you need to do is you need to go down to the motor, set the motor at 230 volt, and then have your electrician come in, put in a double pole single throw breaker, we talked about that last time, and have him hook the pump up 230 volts. Because if you've got number 12 wire, you'll notice at 230 volts we only need number 14. So you are just fine. All right, everybody understand that? When it comes to doing an ohm meter, now we're going to test the pump here. Remember I said you could do live electric tests, and we talked about amp probes and voltage meters. Now we're looking at an ohm meter. There's 3 readings that you're going to get on an ohm meter. One of them is going to be 0. 0 simply means that I have a direct connection, a dead short, or what I like to refer to, a closed circuit. Okay? Another reading that you can get is called infinity. Infinity is just the opposite. I now have no connection, no flow, or an open circuit. If you happen to look in some of the books, we may give you a number. That number is going to fall someplace between 0 and infinity. I was taught a long time ago that if it's not reading 0 and it's not reading infinity, it's going to work. All right? Now, let's do our test here. The first test we're going to look at, here, we're going to do a grounding test on submersible motor. So if I've got a new motor right out of the box, okay, it needs to be able to record 20 million ohms. All right? If I have that same motor newly installed, because I've got that long cable now, it only needs to record 2 million ohms. All right? Finally, if I've got a used motor down in the well, it's going to be 500K, and if I've got a used motor that I've taken out of the well, now I want 10 million ohms. Okay? Now, I've talked about ohm meters in the past because I very, very strongly believe in ohm meters, and the ohm meter of my choice happens to be the Simpson 372. All right? It is an analog meter. Now, let me show you what you're doing here, because besides doing the grounding test, you can also do a line-to-line test. Line-to-line on single-phase 3-wire motor simply means I'm going to connect one of my leads, because remember, you've got 3 wires here. You've got a black wire, a red wire, and a yellow wire. So I'm going to connect one of my leads to the black wire and the other lead to the yellow wire. That's going to give me my main winding. Then I'm going to connect my one that was on the black lead. I'm going to take it off the black lead, and I'm going to put it on the red lead. All right? Again, remember, the red winding is going to have a higher number because of the fact that there is a smaller wire in the start winding. Okay? Those numbers are given to you, and so you want to try to be within those numbers. As long as you are really close, I don't get excited about it. Okay? If you're not really close, then maybe you got a problem. When you do an A.O. Smith above ground motor, there are 5 tests that you can do. You're going to do a grounding test, you're going to do a capacitor test, you're going to do a winding continuity test, you're going to do an overload protector test, and you're going to do a switch test. All right? So let's go ahead and get started. And the first test we're going to do is a grounding test. The important thing to remember on the grounding test, you must have an ohm meter that will measure 1,000 ohms. And again, I just want to remind you that the Simpson 372 will go up to 50 million ohms. If you were to get an expensive digital meter, it probably is going to go up to that also. But when you buy the inexpensive meters, be careful. Sometimes right on the meter it will say 200 ohms. It's not going to do the job. You got to be able to have the one that does the job. Okay? So you're going to connect one lead not there. Yes, that is the grounding screw, and one would think that would be the place to connect, but trust me, you can't. Right next to the grounding screw, you're going to see there is a hole. That's the screw hole that holds the cover on. Connect one of your alligator clips there. Now again, I've always advocated that clipping is much better than touching. But you'll notice that first X there is on A, and A is something you can only touch. You cannot clip. Okay? Then you can clip to L2, and you can clip to L1. There are spades there that you can clip to. So, to go off of A, go to L2, then go from L2 to L1. You should be registering infinity on your meter. There should be no movement at all. If you're using a digital meter, the reading is OL. We'll talk a little bit about that in a minute. You're going to go from that terminal board over to the overload protector. Put your clip over number 1 first of all. Then put your clip over number 2. Then move it to number 3. Remember, the first thing you always do when you take the back cover off the motor is discharge that capacitor by touching one of the yellow wires to that red and white wire. Okay? Again, we learned about that last week. Because it's been discharged, I can go ahead and I can connect my alligator clip here to make sure there's nothing wrong with the capacitor. And finally, I'm going to go ahead and I'm going to clip underneath that rivet, and I'm going to clip underneath that rivet so that I can get right on the spade and get a good connection. And again, there should be no reading at all. It should be infinity all the time. You don't want 0, you want infinity. Okay? If that's what I get on all these readings, I have now passed my grounding test. Time to move on. You'll notice I've chosen the capacitor test for the next test, and again, the reason being is I must have an ohm meter that can read 1,000 ohms. So I come over here, there's a yellow wire there and a yellow wire there, and then there's a white wire with a red tracer there. I'm going to recommend that you take the red wire with the white wire with the red tracer off. Now you can connect to both sides. You've created an open on your capacitor, and now you can connect to both sides. What will happen? You'll notice the ohm meter is on 1,000. The needle will move from infinity to 3. When it gets to 3, it will slowly move back to infinity. Remember, it's 3 times 1,000, so I'm looking for 3,000. When you come to the factory school, I have you do this test 2 more times, and I have you do it the wrong way. I have you leave the ohm meter set to R times 1,000, and we reconnect the red wire, and of course what winds up happening is you wind up getting a 0 reading. Okay? I also have you set it to R times 1, disconnect the red wire, and now the needle doesn't move at all. That's because you're looking for 3,000, and the highest number on the digital meter, the highest number on the analog meter here is 500. So because you can't get anywhere near it, the needle doesn't move. All you've done at this point is you have checked to see if the capacitor is working like the capacitor. To actually check the capacitance, you have to have a capacitance meter. Okay? Now, the Fluke 87V. This is a multimeter. You can hook it up several different ways. The picture right now is designed for AC voltage. You can hook it up so that it will read ohms. Okay? When you set it for ohms, it's going to read OL. With those 2 alligator clips apart from one another, it's going to say OL. What does OL mean? It means open line. Open means there's no connection, and so that means you've got infinity. All right? So again, that's something that you're looking for sometimes, like, for example, when you're doing the grounding test. The other thing I want to point out here is this. If you don't understand what your meter is telling you, you really don't have a meter. So if you went out and bought an expensive digital meter but didn't take the time to learn what the meter is telling you, you really don't have a meter because it can't help you. The whole purpose in having a meter is making sure that you understand it so you know what's going on in that motor. All right? Our third test is going to be our winding continuity test. When you do the winding continuity test, you remember you want it on 230 volts. So if it's at 115, set it for 230. All right? You want the switch in the open position. Again, the best way to do that, disconnect the red and white wire at the capacitor. All right? By disconnecting that red and white wire at the capacitor, you've now created the open that you're looking for. All right? Now you're going to go from L2 to A. L2 to A. Notice you're going through one of the main windings. To get through the other main winding, leave your alligator clip on A, take the one off of L2, and put it on one of the yellow wires from the capacitor. And you're going to go A to yellow. That takes you through your second main winding. And again, these windings should be the same. You don't want infinity and you don't want 0. As long as you're not getting infinity or 0, it's good. All right? The next test you want to do is you want to do the phase or start winding test. To do that, you're going to connect to the red on the switch and the yellow on the capacitor. Notice that takes you through your start or phase winding, and it takes you through the main winding. Now remember, you've got to go through the next main winding with the phase in order to get the same number. So you're going to go red, not to A, but red to L2. That takes you through the phase and the other main winding. All right, the fourth test we're going to do is called the overload protector test. Now remember, the overload protector has a Klexon device in there, and what we're really testing here is, did that device close back up? So you'll notice here, we're going to connect number 2 and number 1. Number 1 is the blue wire, number 2 is the white wire with the black tracer. That's got that Klexon. We should be reading 0. Anything less than 1 ohm is acceptable, but 0 is the preferred reading here. Why? Because there should be a connection. Then don't forget there is a hard wire that goes from 2 to 3, so we move the ohm meter from the blue wire over to the yellow wire. And again, we should be getting a 0 reading because that should be a direct connection there. All right? The last test we're going to do is the switch test. When we do the switch test, what we're going to notice here is that you're going to connect your ohm meter to the bottom underneath. You see where the X is there on the picture. You want to get underneath that rivet and underneath this rivet here. All right? Now, you should be getting a 0 reading because those points that are at the end there should be closed. They're going to look a little bit like this. You need to get your finger in there, and you'll notice where the next red X is. It comes in on that counterweight, and you need to lift up on the counterweight. When you lift up on the counterweight, it's going to look like this, and that's going to open those points, and you should go to infinity. When you let go of the counterweight, it should close back up, and you should go back to 0. And that's your 5 tests that you're going to do on the above ground motors. All right? Now, just a couple quick things here, voltage variance. Motor manufacturers are required by law to build in plus or minus 10% to the rated nameplate voltage. So if we say it's 230, it's got to be able to run between 207 and 253. There are a few places, especially down on the coast of Florida, where they've got some 208 voltage. If you're running 208 voltage, the electric company has the right to do plus or minus 10%, which means they might run anywhere from 187 to 229. Now, of course, the point here is if you run a 230 volt motor on a 208 volt system and that motor burns up, it will not be a warranty. It will not be a warranty. The reason being, it's abuse. If you don't give the motor the voltage it requires, then you're going to wind up having a problem. On startup, remember, voltage drops, amperage goes up. So if I'm running 212, 208 volts, and I start that motor, it's going to drop. And if it drops enough, I'll wind up burning the motor up. So what we recommend is that you use a 200 volt motor, which now operates between 180 and 220. And I'm very comfortable here. I'm not too worried about a 208 volt system going to 229 volts or anything over 220 volts. So I'm usually pretty comfortable putting a 200 volt motor in there. All right? Now, single phase versus 3 phase. This is important. Single phase really has 2 lines or 2 phases. Whether you're 115, where you have a hot and neutral wire, or whether you are 230 volts, where you have 2 hot wires, you still got 2 lines or 2 phases there. Okay? Remember, single phase color, we talked about it last time, is black and white for 115, black and red for 230. We also pointed out that if you're going to use 230 volts, you've got 2 hot wires connected at the panel. You want to use a double pole single throw breaker. Do not use 2 single pole single throw breakers. If you have a true 3 phase, you're going to have 3 transformers on the pole outside. If you have what they call an open or Y delta connection, that's going to have two transformers. Looks a little bit like this. So, of course, the picture on the left is a true three-phase. The picture on the right is that wire open delta. The problem with the wire open delta, I got a call from a guy down in Gurnee, Illinois one time. He was complaining that he burned up two of the motors. Why did our motors burn up so easily? And so I asked him, are you running an open delta system? And he said, what's that? So I said, go to the window and look outside. Do you have two transformers on the pole coming into the building, or do you only have one, or three? And he said, we have two. And I said, okay, you have an open delta system. My suspicions are that the wild leg, which in this case would be line 2, has dropped out, and you single-phase the three-phase motor. And he says, what's that? And I said, well, single-phasing a three-phase motor means that when you drop one of the lines out, motors are stupid. They're just going to keep pulling electric in. So if they say, well, we need 15 amps to do this job, we're going to pull in 15 amps. And so they drop out line 2. Line 1 and 3 says, well, we'll split it. We'll each draw 7.5 amps, and they start pulling more amperage in. And, of course, when you do that, this is the result. Okay? You're doing what we call burning up the motor. And this is a three-phase motor. This is one of his motors that was single-phased. When you look at the opposite side of the motor, I really like this picture a lot because you can see where the wires are candied and where the wires aren't. Where they've got that candy, glossy look, you know those are the burned ones. You can see where the string burned right off of it, okay? If you look down the lower right-hand corner, you see the string is not burned off of it. And, of course, if you look at that very lowest point there, you can see that that's the coil that dropped out. It didn't get hot at all. So the other two overheated because they're trying to compensate for the loss of that phase. So it's very important that you make sure you do not single-phase a three-phase motor. Now, most of us realize that a three-phase motor can run backwards. What's going to happen when it does? You're going to get about half the flow and half the pressure. Okay? How do I correct it? I simply change any two around. So if I take T1 and move it over here, and I take T3 and I move it over there, I have now changed rotation. All right? And once again, if we look at these, you're going to see what's really happening, because what's really happening here is at some point we've got two positives and a negative, and when we change those two wires around, now we're going two negatives and a positive. So at some point we've done that. All right? That's called changing rotation. Now, the last thing we're going to talk about here is imbalance, motor imbalance. All right? This is one of the last pages in the PN 793, and it's an imbalance worksheet. All right? When you look at it, you're going to notice it's on page 87 in the current book. I'm sure that page number is going to change because they added quite a bit to the next book. So that page number will probably change, but it'll still be right towards the back of the book. You're going to find there are three tests that you can do. In the first test, you've got L1 to T1, L2 to T2, and L3 to T3. In the second test, we're going to go L1 to T3, L2 to T1, L3 to T2. This is called rolling the lead. Now notice, we didn't change two leads, we changed all three. We can only do this test 3 times, so if we roll the lead the second time, now we're going to be L2 T1, L1 T2, L2 T3, L3 T1. All right? If I roll them again, I'm back to my original. That's why you can only do the test 3 times. Now, here's what you're going to do. You're going to total up all the amperage that you get on those 3 readings. You're going to do this 3 times because you're doing 3 tests. All right? Then you're going to take the average of those amperage. And we're going to actually work the problem out so you can see it. And we're going to write the deviation between all three of them down here, all right? Once we get those deviations written down, we're going to find the one that's the worst, the one that's the farthest away from the average. So you take the biggest number down here in deviation, and you divide it by the average number of amps. That's going to be your current imbalance. You divide that by 100, that's going to give you a percentage. All right, so let's see how it's done. Here's our first example. In our first example, by the way, if you have a PN793, this is on page 10 in your PN793. You can follow right along with me. In our first example here, we take an amp probe, and notice our readings are on the motor side of the starter. So you've got the electric company side, L1, L2, L3, and you've got the motor side, T1, T2, T3. We're going to work on the terminal side, okay? Notice here we've got L1, T1 at 17, L2, T2 at 15.3, L3, T3 at 17.7. Add that up, I have 50. Divide the 50 by the number of terminals, which is 3. I come up with 16.7 for an average. And if I take the highest one, which is 1.4 amps different, and divide that by the number of amps, average 16.7, I'm going to come up with 8.4%. So I'm 8.4% difference. All right? So we didn't get it, so now we're going to roll the leads. Okay? When we roll the leads and do it again, once again, we're going to take our readings. Now remember, we've changed the readings around. All right? Now we're L1T3 at 16.7, LT21 or T1 at 16.3, and L3T2 at 17. It still adds up to 50. So of course, when we divide it by 3, we're going to come up with that 16.7. We find the one that's the furthest away, and once again, now you'll notice that I'm circling them. It's very important that you circle them. In this case, it's L2T1. We are 0.4 away. If you divide 0.4 by 16.7, you come up with 0.024 or 2.4%. That's really good. That is really, really good. Okay? Anything under 5% is acceptable. Anything under 2%, you're almost silly to continue testing. But I only have one more test to do, so we're going to do one more test. And we're not quite under 2%. So we do the test again. We roll the leads. We take our amp readings here. We come up with L1 T1 or T2 at 16.7, L2 T3 at 16, L3 T1 at 17.3, and again we're going to find our difference, and our difference this time is L2 T1 at 0.7, and so we do the math, and we're 4.2% away. So while we're still within the limits, the last one was a better one, so we really should roll it back to the last one. All right? Now, let's do example 2. Example 2. In example 1, we were able to correct the problem. In example 2, we're not, and that's why this one is very, very important. So, in example 2, we run our test. You'll notice everything kind of comes out the same as the first test we did in example 1, which means, of course, the answer is the same also. We're at 8.4%. Don't forget, circle the one that's wrong. Okay? So this one's no good. We've got to roll the leads. So I change all my leads around. I run my test the second time. I find the one that's the furthest away. This time the one that's the furthest away is going to be L3T2. And you'll notice it's 1 amp away, which comes out to be 6%. Remember, anything over 5 is unacceptable. Can't use it. So we roll the leads one more time. We take our test one more time. And of course, what we find out now is that L1T2 is almost 10% off. So we could not get a good reading here. There's no way we could get this to balance. Because we couldn't get it to balance, what's the next step? Most people are going to say, call the electric company. And with this particular test results, most people would be, well, not most, all people would be wrong. Why would they be wrong? If we look at the test results on paper, it looks like this. And remember, we're going to circle the ones that were bad. And if you look carefully, the ones that were always bad were T2. So this is a terminal problem, which means it's a motor problem. Check the terminal leading to T2 and make sure there's no problems with it. And if there's no problems with the wire going to T2, then the problem is in the motor itself. Call the motor manufacturer, ask them what they want you to do, and then do what they tell you. Just remember this, if they tell you to go ahead and use the motor, they'll get another motor out as soon as possible. Remember, you tell them, put that in writing. Because if it's not in writing and the motor single phases, somebody may say, well, no, he would have never said that. And then you're stuck buying a new motor. Okay? We're going to do the test one more time here. When we do the test this third time, you've probably already guessed, it's going to be L2T2, 8.4%. Roll the leads, do the test the second time. This time it comes up to be L2T1 at 9%. And then we roll the leads. We do the test the third time. And this time the test come up to be L2T3 at 7.2%. So now when you look at it on the worksheet, it looks like this. And again, this is why you circle them. Because when you circle them and the circles don't match up, it's going to be a terminal problem. If you circle them and the circles are all in a row, now you have an electric problem. This is the electric company, all right? What you're hoping for is that it's a simple matter of the electric company has to come out and either replace or tweak their transformer. That's what you're hoping for. It could, however, be this, and this is what you don't want it to be. When they run three-phase, remember, you can take two lines off of three-phase and make single-phase. Hopefully you're doing it the right way, okay? And, of course, once you get that done, then you got U down here on the very end, all right? Now, what do you notice? Let's go back there. Sorry, clicked 1, 2 times. What did you notice here? Well, if you look carefully, all the single phase are using the blue line. So what does that do to the blue line for you? Well, your amps are going to be off. So at this point, there's not a whole lot you can do. Typically what I recommend is put in a variable frequency drive